All righty, let's have some fun. No, that's my iPad's name. No, I just changed it because we're going to be doing some real fun stuff here pretty soon. All righty. So we're working on this. We have a proton moving in Earth's magnetic field. And I've been thinking about your evil twin analogy. You can put that in there. Just make sure you be a little more specific.
Okay.
Yep.
That doesn't feel like I was about it. I don't feel like this is.
Are you telling me that you're a matter supremacist? Against all that, I'm not actually going to say the word because I don't know if people know that word, and it has to be, and I want it to be part of the answer. Okay, so we talked about the velocity of the proton and the magnetic field making a 90-degree angle with each other. I really think you should leave that one alone. Don't look it up.
There's like the editing.
All righty, so this is down, and that's north. So we said that what is magnetic force? Yep. Well, once you get to the 2x2s, V what B?
Oh, I just write parts instead of my.
Well, those are two very different things. One of them is a vector product and the other one is a scalar product. They are two very different things.
I'll have to go back to.
So like if I get an assignment where you have dots where you should have crosses, well, it's not going to be a happy day. I need to come up with something where we use inner products, outer products, wedge products. Have some real fun. All righty, so now for this one, we can say Q BB sine theta. I think a good question for the next assignment is, does this also equal that? That's why it's a good question for the next homework.
It's no.
It's a yes.
Because it's boring.
No. You can prove that.
They don't multiply together.
Yeah, so what happens when you multiply a vector by a scalar? Where does that scalar go? Nope.
Yeah.
Think of the vector in terms of vector component form. Nope. So if I multiply by just some number, where does that number go as far as the components? Yeah, so it goes to each component.
Then you got, see, that's.
mean- Like the first way I wrote it, well, yeah, but yeah, but you'd have to show it as being multiplied into each component. Okay, so that means and since everything is in SI format, what units will this come out in? No. Newtons. It's force. No, I mean, you could go through the dimensional analysis and figure that out, but at the same time, we put everything into SI, so coulombs, meters per second, and Tesla. So it's going to come out to be newtons. Which is weird because Tesla's an electric car, but it's a unit of a magnetic field. So no, but it's not a magnetic car. Okay, so the proton's acceleration. So we have the force on the proton. How do we figure out the acceleration? Mass of what?
Proton.
Proton. And then which way is the force pointing? So you want to think of your angle between the two vectors being there. Now, the way I do it is point your fingers in the direction of velocity and curl them into the magnetic field. Which way does your thumb point? You're using your right hand. It depends on which way you're curling. Fingers in the direction of velocity, curl into the force. If the magnetic field was going down, you would curl that way. Yeah, so that means it's what, coming out of the screen? Yeah, so then what is that? How do I represent that? Dot. So it's a force, it's a vector coming out of the screen. That's why the matrices are better. Have any of you figured out what a matrix is? Yeah, that's not the right answer. What is a matrix? Physically, what does it represent? It's a map of a physical space. So when you go through and you work through the matrix determinant, you end up with a third vector that if you were to map the components of that vector, you would notice that it produces a vector that's perpendicular to the original two in the first matrix. You wouldn't have to use the right-hand rule. You would automatically get a vector in the proper direction. Yeah. Because that's a vector coming out. That's an X. I'd hope you realize that the dot, that's what the dot means. Yeah. The X is going into the wall. The dot's coming out. If you want, you could put K hat. Because you're now working in the Z direction. Well, let's look at this one. Electron moves with the speed of 2.0 times 10 to the 6 meters per second. Why are we writing so slow? I get it now. I'm with you. Most of the time I try not to be rude, but if you open the door. All right, so electron moving, it's moving in a uniform magnetic field of 1.4 Tesla directed due north. At one instant, the electron experiences an upward magnetic force of 2.0 times 10 to the negative 13th newtons. What is the component of the electron's velocity parallel to the magnetic field? No. You're going to have to represent north as a direction and then realize the electron is moving in an arbitrary direction. Okay. No, so what? We'll call that direction north. And the reason we want this represented as a velocity in an arbitrary direction, because we're not exactly working with X and Y, we're working with perpendicular and parallel. That's the velocity of your electron. So then between these two, I have an angle of theta. Now, how am I going to represent parallel and perpendicular? Yeah, and they're going to take what format? Which one of these vectors are they going to align to? The what? The what? Well, they're interacting with the B vector, but so what are they in particular to the velocity vector? Triangles. And that gives us our what? Vector components. I do want to see someday when some of you are working in a hospital and someone says, what's wrong with the patient? Well, you know the squishy thing that's in the place and the thing? Yeah, well, it's not good. Terminology. honestly, if I actually ever had a doctor that said, you know, the squishy thing that's in the place with the thing, I would lose it. Like, so what we have here. So there's your perpendicular and your parallel components. You need glasses. We talked about this. They're not working. See, first off, I could never wear contacts. I can't poke myself in the eye. I just can't do that. You just put a little like a little lens on your finger, think like, no, absolutely not. The doctor who invented those laughed for a very long time ago. Watch what I can get him to do. Now, we can start with I'm going to rearrange this. Why did I rearrange it that way? Yeah, and it becomes what? Mm-hmm. Mm-hmm. So we can figure this out. We can figure out what the perpendicular component is. Well, yeah, that's kind of how you have to do it. You don't really know X and Y are not denoted. You just know that the magnetic field is going north. And V is in an arbitrary direction. So our perpendicular component so I have one of the components. How would I find the other component of that velocity? Using what? Well, yeah, I mean, yeah, it comes out that way, but what formula did we find for vectors using the Pythagorean theorem? What vector formula uses the Pythagorean theorem? It's V parallel, not V11. V11 and V, isn't it V11 plus V upside down T? Like, no. No, well, it is, but come on, it's a real simple theorem that we've used for a lot of vectors. That's for the direction. Yeah, and what does that give us in terms of our vectors? The magnitude. The magnitude of our vector, because if you look, we have that.
No.
All right, so possibly. Yep. Honestly, I mean, I can't make you solve for V parallel. I like, it's just, for me, when I put it on assignment, it's just, it's a strong suggestion. Like, I suggest you do it, because, again, I can't make you do the assignment, but you can't make me give you more than a zero. So it's a standoff.
That is my fault.
This time.
Your answer.
You know what they tell kids in grade school they when they have someone that picks on them all the time, right?
This is like, yeah. Ever at those cat were far behind.
Is hang on, that's oh 9-6. Yeah.
Did you read the assignments with last week? I should have looked read my assignment last week.
You mean the ones that are due like this Friday?
No.
Oh, I saw a bunch of stuff on there. Remind me. Now that I didn't see because I'm into like I've set a block to miss that stuff.
No, you're part of the direction you need.
I don't know. Oh, yeah, it should be first. Yeah, let's switch that around. Hang on, did I do this right in the first place? No, I switched it here. Say that again. Oh, yeah.
Is this? There's no.
No, this is just a magnitude. No, we really can't do that this time because we're not in a specific XYZ coordinate system. Yeah, you could have had north going to the right. You just have to realize you have to set up your velocity vector in an arbitrary direction where you can get parallel and perpendicular components. Okay. Charged particle in a magnetic field. Maybe not exactly what you thought it would do. So first off, if you have a charged particle, so this time it's a negative charge, it's moving in a straight line when it enters this magnetic field, it's going to then experience a force that is in essence a centripetal force or a radial force, causing it to start moving in a circular motion. This is this is the principle behind the mass spectrometer.
There you go, Megatron.
Well, The different masses of the particles entering the mass spectrometer are going to have different radii. What class were you doing mass spec in? Oh, okay. Now, two-dimensionally, you see a circular path. However, remember, usually a charged particle is going to have a velocity vector in a random direction. So when it actually enters the magnetic field, if you look on the right, it's going to have both a parallel and perpendicular component to it, causing part of it to start moving in a circle, but then the parallel component is going to continue to move the particle forward. So in essence, what you're getting is a spiral. Our solar system does something very similar to this. Yeah, but no, I said similar. But like when you have people like, I can predict your future by the fixed unmoving stars. Well, you're going to be wrong. It's like the Great Pyramids used to line up with Orion's belt. They don't anymore. It's because the galaxy moves and we move through it. So you see our solar system. It looks like you go in elliptical orbits, kind of like in a flat plane. Actually, if you watch the solar system move through the galaxy, it looks like a corkscrew. No, no, because we're at a fixed point on the spiral arm. No, the galaxy is the solar system. Yeah, like a corkscrew through the galaxy. Because you are part of it's the same reason as why, as the Earth is spinning, you don't constantly feel yourself being jerked in a direction. You are a part of this inertial reference frame. When you're in your car, you know how you balance out eventually, and you don't feel the cart. That's because you join the inertial reference frame of the car. You don't want to. First off, one of two things would happen. You would like if you exited that inertial reference frame, you could be splatted into a puddle into the ground. You could be thrown into space. They're all painful. No.
What if I'm
Actually, your blood is more likely to boil before you like.
You put it on the inside?
Well, it's more like a high pressure internal system with no pressure outside. You just start to rupture. It takes about 4 seconds to die in the vacuum of space. Yeah, but it's almost like every blood vessel in your body explodes within 2 seconds. If you're in an astronaut suit, it's a pressurized suit. So what is our acceleration equation? So radial acceleration, do you remember how does it relate to velocity and radius of the curvature? Hmm? And we also know that this acceleration also equals force over mass. So we have QVB over M, but for a lot of problems you solve, you're going to need to use the V squared over R equals the QVB over M. That's your magnetic force. Oh, look here. Solve it, Maggie. So the magnetic field used in a mass spectrometer has a strength of 0.5 Tesla. two lithium? I think I mistyped that. What?
Get a present.
Oh, boy.
Yeah, yeah. From all eight trustee members and.
Oh, boy.
Yeah.
Is it something ridiculous that I can wear around campus?
Yes. I forgot it. It's at.
Okay.
4%. Yeah.
So lithium ions with a mass of 6.015 U. What's U? Move through this magnetic field at a radius of 8.4 centimeters. What speed are they moving at? Technically, yes. However, that'll get you like half a point. If I gave you half a point on a problem, you'd lose your mind. So, you what? It better be a good drawing. There is someone in this building who you can recruit to draw real good pictures, but I'm not going to tell you who it is. You're, huh?
Yeah, start calling Dr. Complete.
Absolutely not. If the word dog ever enters my vocabulary, I will jump off the building. Because that means I have degraded to a point that I never thought possible. I don't know if it's as popular now, but when I was in my 20s and whatnot, everyone would walk up like, "Yo, what's up, dog?" I'm like, "Oh, shut up. Just shut up." I can't, absolutely not.
What?
I also, when I used to go to the gym, I stopped going to the gym because of the dude bros. I can't just, yeah, I don't know. What are you doing there, bro? I'm using that spot, bro. I swear to God, I will burn this place to the ground. Although it's worse to be a woman in the gym because they're kind of, you want some help with that? Like you're doing that wrong. Let me show you how to do it. It's like, dude, I'm literally not here to talk to you. Like, why are you? So, how do we solve this? There you go. But the thing is we need a mass that we can use. 6.015 U. What is U? I need this in kilograms. You convert it. That absolutely not. Absolutely not. Here's my thing. I just realized, do you guys know what cheating is? Like, do you know what it is? So if you look something up on AI and then you copy down what it gives you.
Yes.
If you look something up like that and you just copy down what it gives you, that is called what? I really don't think you want to test this one. So I don't care about Siri. I'm going to set off an EMP and I'm going to destroy Siri. Let's do the problem. Okay, so do you know what the conversion factor for 1U is? Okay, and what is U? What kind of unit is that? Which is what's the name of it? You got, yeah, AMUs, atomic mass units.
Is that?
Now, this particle enters a magnetic field. It's a charged particle. We saw on the previous slide what happens in a magnetic field. So, what two forces equal each other? The two forces.
Yeah.
What two forces equal each other? FB is one of them. What kind of acceleration do you have? Radial acceleration. Centripetal force. So, FB is QVB, our centripetal force. So we know our acceleration is V squared over R. We know force is mass times acceleration. So mv squared over R. And you solve for V. So let's see. I mean, technically you would end up with V squared over V equals QBR over M. So V is going to be, yeah, it's the magnetic force equals the centripetal force.
Oh, I'm trying to. I'm trying to do this full time. Open it. No.
Okay, so that lithium ion is moving at about 6.7 times 10 to the fifth meters per second.
A different time.
Yeah, because in this case, it was a +1, so it's a 1e. Yeah, in that case, I mean, you could turn Q into Z times Z, and Z is the magnitude of your charge. It'd be 2e, so you're 1.602, what, yeah, times 2. So you're going to need to have the magnitude of the charge, and everything is a whole number multiple of the fundamental charge. Here we go. A charged particle in crossed E and B fields. Okay, so we have a particle, we have a B field, we have an E field, it's moving at a velocity. We have a magnetic force, we have an electric force, we need a total force. All of these are represented on this free body diagram. Okay. What is the, what equation gives us the magnitude of the electric force? Or gives us the electric force? Let's stick to vectors for the moment. QE. What about the magnetic force? That's not times. That's not a dot. You can't just, you always remember, you can't say times because there's multiple ways to multiply vectors. There's a scalar product and there's a vector product. So if we factor out the Q, we get a very famous equation in physics. You're on timeout for 5 minutes. So you can either write it that way. Or you can write it like that. Yeah, so it's a generalized direction of the magnetic field. This has a name.
What's the name?
Tell me you don't read the textbook without telling me you don't read the textbook. I thought it was appropriate. Just wait a few slides and it will be appropriate. This is called the Lorentz force. No, not. I swear to God. I swear, surely you guys have heard the name of the famous scientist Lorentz. I think I also think on an assignment the second half of the semester we should also work with Lorentz space-time contractions. You guys keep bringing up Einstein, so let's do some general relativity. And that's actually not the full equation. Oh, for the little back row there, talk amongst yourselves. Found out over break, and one of you may have told me this, but I looked into it. Turns out all of Star Wars is told from the perspective of R2-D2.
What, how?
Why can I?
Apparently, it's a story that was retold by R2-D2 because if you notice, he's at every single major event. Yeah, but who could write down what Chewbacca said? So what happened then? It's like, how do you write that? How do you? Also, if you ever want to laugh really, really hard, you remember those music videos where they used to do Follow the Bouncing Ball on the lyrics? So they did one of those for for growl metal, and it was called Growl Karaoke. Oh, it was so fun. No, it's corn. Like Mongolian throat singing? Nice. Throat singing, still better than Taylor Swift. Okay, so Now, there's a simple relationship that we can get to for the velocity of a particle under the Lorentz force. And that's it's going to be okay, so if you were looking at this velocity is going to be in a system that is in equilibrium. So what does that tell us about the force on the system? 0. I was going to use derivatives in extrema, but I figured that would just no. Now that you've asked, you're on timeout again. And what angle do we have where the force is 0? The total force. So imagine a force, well, okay. Let's not do it that way. Okay. What is the angle between the velocity, a particle moving with a velocity v, and the magnetic field? So the maximum force, when you have the maximum force between that velocity and the magnetic field, 90 degrees. So we have a simple relationship here to judge a particle's velocity based on the Lorentz force. Because you notice how when I took it to the other side, it's a negative vector. So we know that the negative vector just flips the vector 180 degrees, but it has the exact same what? Magnitude. So the magnitude still just comes out to be E. Well, so it gets absorbed in there because we know that this maximum force, so we're going to the magnitude that this force. The maximum force is at 90 degrees. Yeah, you can throw magnitude.
Two questions. Millions about his class. Yeah. Oh, I have questions. I said, when are you planning on teaching him? And now